If Максимовский этот самый тоже, тот самый, кто у нас лидер-то?
Okay, so it's my extreme pleasure, and I express my gratitude to organizers to invite me to give you a brief sketch on the problems of beyond the standard model of physics in correlation, in just relationship with questions beyond the standard model of cosmology. The fact is that actually, so I'd like to outline the main message of my talk. It is that our standard model cosmology now is obtains its physical basis beyond the standard model of elementary particles. I'd like to show that inevitably, if you just use physics beyond the standard model of fundamental interactions, you inevitably go beyond the predictions of now standard model of cosmology. And I'll try to give you several examples of this kind of new features, new aspects, and new phenomena, which are all not only interesting by themselves as some exotic and nice hypothetical objects, but they just probably are already discovered. And if it is so, we have a very sensitive proof for both physics beyond the standard model and cosmology, which is based on this physics. So actually, we live in dark universe. We live in the universe full of something dark, what is dark energy and dark matter. And we describe this phenomenon following ideas beyond the standard model of elementary particles. And there are three basic elements of now standard cosmology, which involves inflation, baryosynthesis, and dark matter and dark energy. Actually, cosmological consequences of particle theory, they just in fact reflect the fundamental structure of particle theory. So that actually in order to be candidate of dark matter, you need some conservation law which makes particles to be stable, because they should survive to the present time. And because of that, you just relate the hypothetical candidates for dark matter to the new symmetries which provide such conservation law at the microscopic level. Breaking of symmetry and mechanism of this breaking can lead to phase transitions in the universe. And this phase transition can give us some hints in the topological defects. And there may appear also structures which reflect the processes which indicate possible strong inhomogeneity of very early. So as concerns dark matter, the main idea of its existence comes from the relationship. Well, there are many observational evidences like rotation curves of galaxies, like dark halos of galaxies, effects of macro lensing gives us information that something is present beyond the visible matter. But however, I think that most important point is that we need something what triggers development of gravitational instability in the period when baryonic matter was ionized and could not participate in this process, so that only assuming that there is some fraction of matter which decouples from matter and radiation, only under this condition we can just explain why the structure is formed at the observed level of CMB anisotropy. Actually, all the candidates matter just possess this property that they have some new feature which follows from the symmetry of corresponding body. So just the simplest way to consider dark matter candidates is to assume that they are massive and weakly interact. Then naturally such gas was present in the universe, it was frozen out, and then just it starts to dominate and form a large-scale structure, and the scale of the structure is determined by the masses of particles. However, and that was the origin of the miracle, which was the mainstream of dark matter searches for last decades, because if you take weakly interacting massive particles with masses at the range of tens, hundreds GeV with weak interaction cross-section, you number density multiplied by their mass in the modern universe, which explains the measured dark matter. So the question was how to look for these particles, but actually the problem is that no convincing argument for existence of them appear in underground detectors, as well as the natural way to explain WIMPs was to look for lighter supersymmetric particles, and no supersymmetric particles at scale were still found at LHC, and it makes us to go beyond this simplest way to find reasons for dark matter, and we come to many other candidates. Some of them were discussed today, like sterile neutrinos. It's also axions. There may be not 100 GeV scale supersymmetric candidates, but sub-Planck scale, which, however, gives us the possibility of supergravity, Starobinsky supergravity, for example. And what I'd like to discuss today is just that there is a possibility that in principle such particles can be strongly interacting, and that can explain the puzzles of direct dark matter searches. Just to mention, first idea to search for dark matter candidates when there was no term of dark matter. It was master's thesis of Schwarzman, which we made him to publish in 1982, which considered the possibility that massive neutrinos, if they have mass of 10 eV, they may have coherent effect, which causes some dynamical possible acceleration, which made them measured. However, now we are talking about, if we're talking about weakly interacting massive particles, the recoil will be significant, and it is the aim of the underground experiments of such recoil. And however, there are two different types of experiments. One of them is just to have installation deeply underground, to use radioactively pure materials and try to find effects of such recoil. However, if you take annual modulation of this effect, which is related with the rotation of Earth around the Sun, then you may reduce many background effects. You lose all the data, all the events, but the events which collect, in this case, just are more free, liberated from the effects of background. And they are very popular. It's not the last picture which people demonstrate. And they show that if it is WIMPs, then it is strange, because there are positive results of Dama sodium iodine, Dama Libra experiment at the level of 12 sigma. They claim that they have positive effect. And those who look for WIMPs, they don't see anything in the ranges of different masses. And probably it is because we look for WIMPs, while dark matter is not necessary WIMPs. And the same, well, should be dark, so neutral. But it doesn't mean that it cannot consist of charged particles. And in the same way as ordinary atoms consist of electrically charged nuclei and electrons, in the same way, it is possible to have charged particles which bind in neutral atoms. There is principal point that if these charged particles have positive charge or odd negative charge, if it is positive charge, they bind with electron and form corresponding anomalous isotope. If they have odd negative charge, then they could bind with primordial helium and form +1 ions, which just misbehave like anomalous hydrogen. Only if the particles have even charge, such evident contradiction is avoided. And if you take and the properties of such atom, which I call dark atom, is very non-trivial. I'm sorry, just so here formula which indicate that the size of the Bohr orbit of this atom just is equal to the size of helium nucleus. So actually, you have atom, you have everything except for this hypothetical particle, known laws of nuclear and atomic physics, but the combination of these laws is completely non-trivial in this case, and it leads, well, there are many candidates for that, and it may be either directly lepton-like particles, or it may be clusters of heavy quarks, which so it's easy to understand that if you have quark with mass above 10th GeV, then it can bind by chromocoulomb force much stronger than by confinement. So if top quark was sufficiently metal stable, we could see formation of a TTT object, which has size and much smaller than the size of confinement. So it's not hadron in that sense, but it also indicates at present we cannot create objects at the accelerators. But if there are new quarks which are stable, sufficiently long-living, then such objects can bind with the helium, and the most interesting case here is working technical model, which is also nicely related to the problem that if you have no supersymmetry at the if you don't have supersymmetry at large at the 100 GeV scale, then just how we can solve the problems of standard model, which are naturally proposed by supersymmetry, because it explained us why Higgs mass is stable. It explained us why the electroweak scale has appeared, and the alternative way is to have a composite nature of Higgs boson that gives us the scale of electroweak symmetry breaking, as well as it gives us the possibility to solve the problem of Higgs mass divergence, simply because it is composite. So this composite model just assumes that there are some constituents of this composite Higgs, and these constituents may be charged, and so charged anti-charge are just charged, anti-charged, just give you neutral state, and if you are charged, bound by the same binding as it is, for example, for the technical model, then just have multiple charged particles, and actually global written global anomaly avoidance requires some charge assignment, and this charge assignment, however, leaves various possibilities for absolute value of these charges. And the interesting point is that since it is related to electroweak symmetry, so that you have SU2 spherons, this spheron transition makes possible to equilibrate the excess of particle of this new stable multiple charged particle and the density of baryon excess. So you have relationship between baryon asymmetry and technilepton and technibaryon asymmetry. It's responsible in this case. The charged particles are not only -2, but they may be -4, -6, -8. And then you have in early universe, if you have excess of this species balanced with baryon asymmetry, then you have this excessive negatively charged particle bound with corresponding n. So it is, if charge is -2n, then n nuclei of primordial helium should bind, and you have n alpha particle nucleus, like for example, if n equal to 4, then it is oxygen nucleus in which you have negatively inside of which you have negatively charged lepton, like, because it is really lepton here, it has no TCT interactions. So inside it, and it is Thomson atom, but very non-trivial form. So that is the main technical problem of analysis of this model. But this model just gives us explanation that actually such dark atoms, they decouple from plasma at the temperatures above 1 keV, because plasma energy and momentum transfer to this gas becomes ineffective, and so it decouples and plays the role of dark matter, which is, though they are TeV range objects, they are not strictly cold dark matter because there is some suppression, but not as strong as warm dark matter. But so it's some warmer than cold dark matter scenario, and it can be ionized. And you have new component of multiple charged particles in cosmic ray, and in Earth, it's evident. So if you take average density of baryons in the galaxy, then it is transparent for that. But if you take the more or less dense object, which dark atoms are captured, and so the same happens in Earth. But in Earth, you don't have WIMPs which penetrate freely through the terrestrial matter. But they, these dark, strongly interacting dark atoms, they are slowed down in atmosphere and then in terrestrial matter, so that they diffuse with thermal velocity towards the center of Earth. And at each level of terrestrial matter, you have a equilibrium concentration, which is balanced between the incoming flux and this downstreaming diffusion. And it gives us, so it makes impossible to use recoil because there is no recoil from them. But there is a possibility to explain the effects which are observed by gamma experiment by a specific type of interaction with dark atoms present there. Coming from the incoming flux and are present in the device and matter of this device, because these number density there is just regulated by the incoming flux. And because of that, you have annual modulation of this number density, so that we can explain the effect which is observed as annual modulation by annual modulation of this inelastic process in which this dark atom binds with nucleus, but not at the level of nuclear fusion, because if the nuclei and or helium or that atom bind completely, then just you have energy release in the MeV range. However, the positive result comes from the range from below 6 keV. And the qualitative picture, which is assumed here, is that at large distances, you have Stark effect, which makes this dark atom polarized so that there is attraction. At some moment, nuclear force makes helium shell to turn to the oncoming nucleus, but then Coulomb force makes it back. And that is the main crucial point which we are studying now, because our phenomenological hypothetical description was that you have such an effect of effective dipole barrier, which prevents dark atom merge with nucleus. And so you have a shallow well in which you may have level of few keV, and our idea was that sodium nuclei have such a bound state, and just the transition to this bound state gives us, we can use here, if such state exists, then we can use the analogy with radiative capture of neutron by proton, impair the gamma radiation, and taking into account that this helium system is this dark atom system cannot possess magnetic dipole moment, and the electric dipole moment is suppressed, we can simply reproduce the number of events observed in Dama experiment. However, there are several open questions in this scenario. The most crucial is the question whether this potential barrier really exists, because we could not prove it by methods of perturbation theory, because it loses its validity just in the moment when you really should understand what happens. So now we are turning to this problem in different ways, but simultaneously, this hypothesis puts forward the question how we can probe at colliders this hypothesis. And it is clear that it's not the same as it is usually drawn, that you have to observe missing mass and missing energy and missing momentum, standard model interactions at the collider, because here you need stable charged particles and search for multiple charged particles just moves the lower bound for the mass of these multiple charged particles at the TeV level. And actually, this hypothetical phenomenon just gives me an opportunity to mention several non-trivial things which we should take into account in our analysis of the
Does anybody else hear the speaker?
No.
just a moment.
We have lost
Okay.
sound.
Sorry, now do you hear me?
Yes.
Now, yes.
Okay, sorry. So just to draw attention that here the message, another message is that actually when we talk about astronomy as the proof for different cosmological effects of new physics, actually we can use multi-messenger cosmology, which gives me just a moment. Which gives us possibility to consider not only the basic necessary elements of cosmological construction, but also to use the byproducts. So, for example, you have some stable candidate of dark matter, but it should be accompanied by unstable candidate, and its decays before the modern stage of cosmological evolution can lead to changes in primordial light element abundances, in CMB properties, or just in some new sources of cosmic radiation. And here, non-equilibrium particles are especially important. Just let me note that people discuss primordial black holes as macroscopic candidates for dark matter. And well, there are many figures which just demonstrate possible constraints on dark matter or on primordial black holes as dark matter candidates. And the idea is that primordial black holes, even if they are absent, can provide us non-trivial information about early dust-like stages, about first-order phase transitions. Effects of primordial black hole evaporation can put constraints even in case primordial black holes do not survive to the present time. And what is interesting that it puts forward the question to what extent our modern concept of homogeneous universe is strictly so, because we need some fluctuations in order to create observed structure. And in principle, we can have components which are subdominant, which contribute in total density at very low level, but they give us possible strong non-homogeneities at smaller than just megaparsec scales. And there are two principal possibilities for that. One of them is that it is some effect of cosmological phase transitions, which can lead unstable defects, which are reflected in primordial nonlinear structures, like primordial black hole clusters, what I call archeoles. So here it is important that if we have a Higgs potential, then it is modified at high temperature, so you have restoration of symmetry at high temperatures, or if you have in zero temperature, but you have inflaton interaction, then you have also some critical value which gives you phase transition. There may be different topological defects, and the simple example of axion-like particle models give us illustration that if the first phase transition takes place after inflation, then you have a structure of cosmic strings, which after the second phase transition is converted into wall surrounded by string unstable defect. These defects disappear, but they leave the distribution of energy density, which is correlated along the initial directions of strings, and strings go to, in fact, formally infinity. It's not infinity, but it's just that part of multiverse in which we had experienced state. Another possibility is that the first phase transition takes place at inflation. And if it is so, then you don't have strings because you have at the e-folding corresponding to the third part of the universe some fixed value of phase, and this phase then can fluctuate. But if it fluctuates to a value larger than pi, then you have two vacua which just are separated by wall, which is by this construction closed. You have a system of closed walls, and this system of closed walls at their collapse create massive primordial black hole clusters, and the properties of these black holes are determined by the fundamental scale of this model, that is the first and second energy scale, so that the is determined by the condition that the wall the thickness of wall should be smaller than the gravitational radius, otherwise the wall inside its gravitational radius, and the formation of these walls and can lead to the primordial gravitational wave spectrum. But also you have discussed today, so only draw attention that gravitational wave astronomy just gives us an interesting possibility to find explanation of binaries which are in such clusters. Certainly, if you have clustering of primordial black holes, then you can make binaries much easier. And also the masses, which can hardly be explained by collapse of primordial star, first general third population. It is there is collapse, and there is positron instability, which just makes impossible to collapse to the black hole with mass above 50 solar masses, while there was an event which looked like collapse of more massive black holes, and authors mentioned my works in this aspect as possible explanation. And let me come to the final part of exotics which can appear and accomplish our vision of the universe, related with the question that whether we cannot have macroscopic antimatter in baryon asymmetric universe. And the answer is that any model of baryosynthesis can predict some amount of macroscopic antimatter if it is strongly non-homogeneous. If it is strongly non-homogeneous, then have different excess of baryons in different places. And if the extreme case, it changes sign. So the same mechanism gives you dominantly baryon excess, but in some places it is anti-baryon excess. And so just the only condition is that the macroscopic region should be sufficiently large not to be eaten completely by surrounding matter, because there is diffusion of the border and annihilation. And this annihilation should lead to just vanishing of the domain, which is smaller than something like in anti-baryon mass, smaller than anti-baryon globular cluster. And if you have such an antimatter globular cluster in our galaxy, then just if it evolves in the same way as ordinary matter. So if you assume that not only the physics of antimatter, but also initial conditions were more or less similar, then you have a possibility to have such globular cluster with antimatter stars, which evolve like stars. Just note, it's not necessarily the case, because you may have much higher densities in the antimatter domain, as well as the surrounding matter can be much higher than average density. And this resembles me the approach of Snowden of we consider very dense antivariant objects. However, if it is just more or less looking like normal antimatter globular cluster, then it should have stars, anti-stellar winds. They annihilate you and galaxy by anti-fly, and then you have an annihilation which is constrained by gamma ray background, and there may be also flux of antinuclei. And our idea is that anti-helium is most stable because, first of all, it should be the second factor anti-hydrogen element in the anti-barrier nuclear synthesis. And second, any process of evolution leads to heavier nuclei, but they, inside antimatter stars, when they explode, heavy nuclei like heavy anti-iron just moves in the interstellar matter of galaxy, annihilates, and it is destructed, and a lot of anti-helium should appear. So if we take it into account, then just that antimatter globular cluster is in halo, then just it should somehow move here, and we study now the propagation of antinuclei from such local source. There is a serious magnetic cutoff at the border of the disk component of the galaxy. However, on the other side, though you have this cutoff for lower energy, we can expect that the spectrum initial should be just dominant at low energy. So actually, taking into account this cutoff, you should have something like, you should have, in fact, something like just predicted to be a maximum at the scale of tens GeV. And 17 just has shown, he didn't publish it, so just please just be accurate and don't use this figure anywhere, because just simply taken his presentation in CERN. So in his first presentation in 2016, he has just demonstrated something what looked like anti-helium 3, and after that, 2 years later, he talked about 8 clear single tracks with -2 charge and with within helium mass, and even something like anti-helium 4 appeared. However, its probability that it is not not background is rather low. Is really some candidate or some event. However, the important point is from all this, if we can explain the puzzles of direct dark matter searches by dark, if we can explain the observed data, observational data from gravitational wave sources, so that it is massive primordial black. If we can, if we really can have in next few years confirmation anti-helium component is present in cosmic rays. Note that any extra pair of nuclear and anti-nuclear pairs of secondary origin is suppressed by factor of 10 to -4. So at the level of 10 to -9, we can expect some visible signal in IMS experiment. So if you have anti-helium free theoretical estimations 10 to minus 12, it's highly improbable that natural sources can give something in IMF. So if they do observe something, it should be something different from natural explanation from cosmic ray interactions given to segments. All that, however exotic it is, in that sense, and maybe fine-tuning, but actually such fine-tuning gives you a fine, sensitive proof to parameters of new physics and corresponding cosmological scenarios. So if we need anti-matter domain generations in the universe, then you just rule out most of models we don't predict. So you can concentrate on specific type of classes of models and their parameters. So this is the basic idea of cosmological physics, which helps us to specify relationship between beyond the standard model physics and
So thank you very much for this comprehensive review. We have a couple of minutes for questions. Let's start from the audience. Yes.
Maxim, thank you very much for a very nice presentation. But you have developed so abundant picture that it's difficult to choose something definite. But nonetheless, I'll try. You argued about dark atoms. Am I right that dark atoms they are bound by electromagnetic forces anyway? Okay.
yeah. They are atoms in that sense because they are bound by Coulomb electromagnetic interaction.
In this case, as normally, you know, they have to have a kind of van der Waals forces, residual forces. And in this way, I think that, for example, electrons can be easily interact with them. And also we have some kind of magnetic interactions as well.
The basic problem of this scenario is the complicated analysis of these dark atom interactions, because you have no simplified assumptions which we use in atomic physics. In atomic physics, we have small nucleus as compared with Bohr orbit. We have electroweak interacting shell. Here you have Bohr orbit or simply Thomson atom within which you have left. And so actually the basic problem which we want to solve is, well, in principle, it should be described properly by quantum mechanical means, because all the physics in principle, but how to do it, it's again very complicated mathematical problem. As soon as we just find the correct and comprehensive analysis of structure of dark atoms and their interaction, then all these phenomena should be immediately analyzed. I agree that there should, well, first of all, I didn't mention it, but one of the possibilities was that dark atoms interact, well, they are non-interacting gas at the scale of galaxy. But if there is some density, increase of number density of dark atoms, then you have enhancement of their rare collisions. So if such collisions take place in central part of galaxy, then they are excited, and their de-excitation from 2s level to 1s level, that is E0 transition, just leads to electron-positron pair production. And this positron annihilation line was observed in integral in excess as compared to natural. In order to explain it, we should assume something about mass of this particles. It turns out that the optimal effect can be reached for masses which are within the reach of LHC. So actually, this type of explanation can find experimental proof in the LHC sources searches for stable multi-charge particles. It is just at this 1.3 TeV range is the optimal mass for these particles, which can explain this excess of electron positron annihilation line in the central part of galaxy. And it is just within the reach of analysis of combined CMS and
Okay, thank you very much. Thank you.
Okay, thanks. I think to fit into the schedule, we should post further questions to Zoom chat and discuss them later. We have no time for further questions, unfortunately, so please post them.
well, I will stay until the discussion and I'll be available. Okay.
Yes, thanks. Thank you very much. Let's proceed to the next talk on Higgs scalaron inflation.